Okay, so our second speaker today will be Christian Copetti from SISSA, and he will tell us about condensing and factorizing in low-dimensional gravity.
Okay, so can you hear me fine? Yes, no? Okay, that's great. So I'm going to talk about, okay, first let me thank the organizers to giving me this opportunity. It has been very nice to be in presence again, talking to real people for some weeks. So I'm very grateful for that. I'm going to talk about this upcoming work with Francesco and Lorenzo. I think it's going to be kind of an informal presentation. I try to put not too many technical details. So let's go. So what are we doing? So first, like a bit of motivation. Like during the last years, starting with this seminal work by Saad, Schenker, and Stanford, and a lot of follow-up papers, there has been some interest in studying gravitational path integrals in low dimensionality. One of the messages that you get from workable examples, for example, the JT gravity, is that these path integrals, which are maybe semi-classical in nature, seem to actually describe an ensemble of dual theories in the holographic sense. So the theories that live on some fixed boundaries. And the way they do it is by having some wormhole configurations like this. So this is one-dimensional. So this is S1, and this is the wormhole configuration, which connect the two boundaries. And those are thought as some statistical correlations between the okay, they told me about this, kind of getting worse. Okay, between the boundary CFTs, and the holographic dictionary for this theory should be interpreted as having a dual ensemble of quantum field theories. So okay, there is a way to formulate this slightly more precisely, I think, due to Madolf and Maxfield, and following the seminal work of Coleman, who was the first to study this kind of wormholes in gravity plus quantum mechanics, quantum field theory. So you can think of some third quantized picture in which you have some gravitational path integral, which I denote with this blob, but it's hard to define precisely what it is because they're summing over a lot of geometries which are closed. Okay. And you have some boundary operator, like this Z, which creates an holographic boundary M and adds it to your gravitational path integral. So this is like the cartoon. You can show that these operators commute, so you can diagonalize them on the Hilbert space of disputative quantum gravity theory, which it's hard to define, so it's just a formal reasoning. And let me denote this. Okay, let's see, this goes away. Okay, yes. Let's denote a basis of this Hilbert space by, okay, yeah. By alpha, okay, and since, okay, well, you remember what it was written, so, okay, now I don't move, and the eigenvalue of this partition function by Z alpha, and we will call this alpha eigenstate, so it's just terminology. So there are two cases, either there is only one alpha eigenstate or there are more, okay? When there is more than one, you can compute some correlator of these boundary creation operators in the quantum mechanics and use a completeness relation to put this alpha basis inside. And you see that this splits as a direct sum over the alpha eigenstates of the eigenvalues with some factor which is positive definite. So if you normalize in a clever way, you get a probability density. And this is like in quantum field theory, this is just like when you have super selection sectors. So cannot pass from one alpha eigenstate to the other by using these boundary creation operators. I think this is like the most familiar version of this. So one of the points of this talk is trying to understand whether and how this alpha eigenstate can be given a geometric description, like a path integral description. So how do we prepare them? Because we've used some very non-perturbative ideas here in the definition. In 2D, there are some proposals which seem to work quite well, which involve d-branes in JT gravity, essentially. And I will comment about how this connects with what we will say afterwards. But in this talk, we are going to study 3D theories. These are going to be like toy models. So I'm going to explain where the ideas come from. So last year, there was a paper of Maloney and Witten who tried to reverse logic. So you start in 2 dimension from some ensemble, you just create it, try to write its partition function and something that looks gravitational in nature. What they use is the Narayana ensemble, which is just an ensemble over essentially n free bosons, which have a class of marginal deformations labeled by the metric and the B field. Of course, you have to divide by dualities, identification, so it's some kind of homogeneous space. And they used as a probability measure just the volume element, which is a homologic of metric. And using some, they use some differential equation. They wrote down some differential equation that this function has to satisfy. And they wrote down a nice expansion for it. So in this talk, we're just going to talk about torus bound, essentially. So I'm going to just fix this notation for now. And what it turns out is that you can write the partition functions single boundary. You can extend to multi-boundary, but it's a bit technical, so I won't go into the details. As a sum over certain elements of a coset, SL2Z mod this gamma infinity, I will explain what it is, of some certain, in this case, essentially vacuum Virasoro characters. You can also, I think it's also very natural to interpret them as some L to the N Chern-Simons, but okay, maybe I will talk about this later. And why is this gravitational? Because you can, okay, let's see what is next. Okay, you can think of each of the terms in the sum, so each of these gamma, the small gamma, as a filling of the 2-dimensional torus by a 3-dimensional handle bodies. So the gamma essentially labels the cycle which is contractible. And this quotient is because the vacuum, so the 0, 0 character, don't see the whole SL2. Some SL2 transformation will leave this invariant. So this geometry identified, essentially. So we'll have this kind of generic sum. And formally, to each of these, you can associate some kind of geometric picture. So it's a sum of geometries. The interpretation in gravity is not super clear because, of course, there will be different theories that have this as the vacuum ADS contribution. But I think a rather natural one is this sorry, just not chiral, Chern-Simons theory. But okay, this is just motivation. So what we're going to consider is a more controlled example in which we take, for example, G level K times G level minus K Chern-Simons. So it's the number of states is finite here. And we take a similar gravitational sum. So we're going to do something like this. But now this gamma prime is a bit different because it depends on the bulk Chern-Simons theory that you have chosen. But you can define it in every case. Okay, just a bit of notation. So essentially, to make contact with this in the bulk, one usually puts holomorphic or anti-holomorphic boundary conditions on the boundary and sees the character as a superposition between states in which you have put a Wilson line. So this is not very precise then. You have to put non-chiral theories, otherwise this is all ill-defined in some sense. There are gravitational anomalies, and you compute an overlap between this path integral and the prescribed holomorphic, anti-holomorphic boundary condition. So there is a clear way to say what this guy here is. Okay, so essentially in the long story short, in the gk times g minus k, this setup, this is, okay, just to be clear, this is a solid torus. So this is identified, these two ends, and this is in the non-contractible cycle in the center. So sometimes I will just use this notation in which you don't put an S1 because it's simple to draw. Okay, so the dictionary is essentially that the overlap between this kind of states and the boundary condition is a character in the LCFT. So the gravitational path integral that we're going to consider is a sum of this kind of overlaps. Just to explain the notation, so here in this basis, I also identify the cycle gamma where I put the Wilson line. These are just different choices of bases which are related by the modular transformation. So it's useful to just write the sum in a kind of more compact way, but you can think of it, you can just think of this identity as defining what we will need for this sum. And again, you have to do a different quotient, which depends on the CFT, but most of what we will say will not depend on this kind of quotienting procedure, so you can kind of keep it in the back of your head. Okay, so now I have to make some digression about so this procedure will always give you a modular invariant answer by definition. It's how we do it. We sum over the images, so it's modular invariant. But there is another way to construct modular invariance in CFT, which is the usual way, you know? And the usual way is to define a mass matrix. So this is a matrix Zij bar, which depends on some choice, modular invariance A, which has some property, you know, and couples the left and the right moving parts of the CFT. So the property are very natural. One is that these guys are integer and positive, so they compute dimension on some Hilbert spaces, essentially. We want uniqueness of the vacuum, so this is okay in the cases we are going to study. In some cases, you can have like the twist sector of some Hilbert space, then you don't have like essentially some kind of different version, but in the simple cases, this is what we're gonna use. So uniqueness of the vacuum, and then you have modular invariance. So T transformation, but that's much simpler. So I didn't write it down. And this have a well-known classification, for example, in the work of Andrea, which is not here, but the punchline of this is that for a given set of LCFT characters, so if you fix the chiral algebra, you have in general more than one way to make modular invariance. And I will use this slightly different. Okay, I shouldn't have gone so low. I will use this slightly different notation in which I just put the two indices in one index because it's going to be more convenient afterwards. So just remember that every time you see a small a index, you can think about Ij bar index, and it's a vector that transforms as one like fundamental index, and one is the conjugate representation. So it's but it's an invariant vector. It's equivalent, but it's a bit more compact. Okay, so then you can say, if I have these building blocks, I can expand this guy in these functions. And this was done for the first time in this paper, 2011. But essentially, they studied the opposite of what we're interested in, because they studied when there is only one term on this side. This was the focus. And these authors here did this kind of sums for some fixed theory, for example, SU2 level K, SU3, so some cases which are under control. And in general, you're going to get a linear sum of this physical modular invariant. And sometimes you can get some non-physical terms. I just mean that this Zij is integer but negative. So in the formulation we're going to give, you can somehow take care also of those, but it's not very natural. So we're going to just think of the cases in which these are positive quantities and you don't have non-physical guys. But it's important to understand when this does not appear and when these PA are positive numbers. So but maybe I will comment at the end. It's not a very simple question to answer. But what we want to do is to interpret this from bulk ADS. So to say, how should we think about this sum in the bulk? And since this look like the alpha eigenstates, no, because it's a linear combination of these guys, can we define what it means to pick one of them? And does this solve factorization? How? So this is kind of the question. Okay, here is what I said before. So the summary of what we're gonna say is that an alpha eigenstate, in this case, can be described by condensation of certain class of defects, which I will make more precise. So when you have done this, so this is like the cartoon, these are the defects. If you try to compute a wormhole, you can cut it out and absorb this state, which is also a defect, in the gas. And then you just get the geometry, the disconnected geometry you started, which is factorized. And then, so in some way, these kind of wormholes are equivalent at the quantum level to a disconnected contribution. So I think I should say something more, because otherwise it's a bit unclear. But essentially, in my mind, there are two ways to get out of this factorization problem. The problem is just that once you sum over configurations, you have some that fill the separate regions, no, like this, and plus work configuration, not better specified, okay, which you want to cancel, no? So there are like two ways in which you can do this. So either this is zero for a reason, no? Okay, for this happens a lot if you study supersymmetric example. Then this direction, you make it periodic, and you will have a zero mode, usually that remains around the throat, and this gives you the zero. So in this case, the wormholes are there because you have fermionic zero modes. And is that while these configurations from the semi-classical point of view seem different, no, because just write the gravitational geometry, when you put quantum fluctuations on them, they actually become equivalent, so that they compute the same thing. So they are different, like different backgrounds that you can start your computation from, but you get the same answer. So you shouldn't overcount these backgrounds. This is the case we are going to find in this talk. So this is possibility, no? This. Okay. So I have to explain what is a mass matrix. So this is like the short version, and then I'm gonna explain what the words mean. Okay, this is understood in mathematics. So as this square says, it's isomorphic too. So you have to explain how you do it to the condensation. So it's what I call gauging of a commutative Lagrangian. Here I have to add some adjectives, but I'm not gonna be super precise. I'm gonna talk about the most important properties and why we want them. Otherwise, it becomes very technical. Algebra, so we're gonna explain why you talk about algebra in the full category of the lines. So here are the chiral ones and the anti-chirals. So this is just the lines in Chern-Simons, one for each chirality. You can do the same thing without having this kind of structure. You can have only one whatever topological field theory, but then you have to ask about canceling the gravitational anomalies. So essentially, in that case, it can happen that there is no modular invariant, so the gravitational theory will give you 0. And in this case, there is always at least one, which is a diagonal one, so you never get 0. But modulo these subtleties, you can just study this in the same tools. And this, I think, is understood from early work of Fuchs, Runkel, and Schweigert, and a lot of follow-ups. There is a very nice paper by Kong in 2013 who explains why you should think of this structure as describing gauging of something, which was very unclear to me. Then two very nice Kapustin and Saulina, also from 2013 or 14, who explain how you should think of this in like quantum field theory, and a lot of very nice correspondences. And the recent work of this year by Kaidi, Komargotsky, Omori, Seif-Nashri, and Shao, who explain this in give some necessary and sometimes sufficient condition to classify when this kind of object exists, essentially. So now I'm going to just talk about of generalities, but you can also see these talks of the same workshop for similar concept, essentially. So I will not spend maybe too much time on that. Yeah.
So, so in the algebra that defines the mass matrix, is that the conditions on the algebra, is it same as the condition of Lagrangian algebra, or is it slightly less constrained? Like maybe the Fuchs-Schweigert paper, maybe the number of times the identity can occur in the algebra is, I mean, I remember the algebra that defines a partition function to be a
no, yeah, there is a bit of mapping between this and that construction, which is essentially folding trick. But if you have a commutative Lagrangian algebra, you always get a good modular invariant, and vice versa too. So,
I see. Yeah, I mean, yeah. Sorry. Lagrangian algebra to the mass matrix is kind of okay, but I was thinking the opposite direction, because I also think it's the opposite direction also works in abelian cases, like when the chiral algebra is, you have primary operators with abelian fusion rules. But yeah, maybe I'm misremembering.
No, but I will talk. I will say. I mean what I mean. Maybe the idea is just that you identify these elements from the partition function of the gauge theory. But okay, depends then how much in depth you want to go, maybe. So it's gonna be like a contained statement, let's say.
Yeah.
But I think with some assumption is like an if and only if. But okay.
Thank you. Yeah.
Any more questions?
If I can just add a comment. So if you look at the face of it, the construction of Fuchs looks different in the sense they don't have a commutative algebra. They have a non-commutative algebra. But this doesn't live in C times C bar, lives only in C. So at the end of the day, it's equivalent, but the construction looks different.
Yeah, I won't talk about this, but if you come afterwards, I explain, because it takes like 10 minutes. But just a brief recap to fix a bit the notation and so on. So modular tensor categories with just the mathematical structure that describes what the lines in Chern-Simons do. So, I mean, probably we have already seen this in some talks, so I will go quickly. So lines are thought about as object in these categories. So I will just draw them like this. Usually we'll forget the arrows, but you just read the figures from below upwards. Okay, this is the convention, so I don't have to draw arrows. you have maps between lines, which are usually called morphisms. There is some kind of that lives here when three lines cross, and it may be more than one dimensional, so you have to put an index here. And in the presentation, we will just think of it as one dimensional and drop the indices, so the formulas become easier. But they also work if this is not the case. It's just a technicality. And there is also some kind of dual morphism, which does the map in the other sense. So you have these ways to attach three lines. And it's useful to decompose lines into simple ones. And simple just means that if you try to make a map from one to the other, there is only the identity times the delta. So if you take a direct sum, you can always project on one component. No? So this is a map from the line to another. But if you take the components, you get the simplest constituents. So A, B, and so on will be the simple lines. And X, Y, Z will be normal lines. Okay, this line has some fusion, so you can bring them together to get a direct sum of lines. So you define some kind of algebra and times some integer coefficients. And this coefficient just tells you how many maps you have. So how many maps you have in this trivalent junction. So the dimension of this Hilbert space, if you want. So when we don't write these indices, just mean that this guy is either 0 or 1. Okay. Then you can associate some quantum dimension to these lines, which I denote as dA, which is just a one-point function of the line closed. It's just graphical notation. And the important thing is that this is an associative algebra. So essentially, it means that you can relate the product. This is a product. Where's the stroke? Okay, yeah, this one. Okay, in the left, so you are going to kind of A cross B cross, and you cannot see now, I have to do it bigger. A cross B, and you can either do it like this, or you can do it like this, no? So it's associative. And so there is some kind of invertible map, which is this F matrix that relates the two ways of doing it. And there's some consistency condition on this, so this pentagon and hexagon equation that tells you that this associativity is consistent. Okay, then we will have, since there is a modular tensor category, we have a notion of braiding lines. So we have another matrix that relates the two lines on which cross in this way to having the lines just coming in. And you can write it in components. So this is going to be R, A, B, C times this thing. And with this, you can build essentially the spin of a line, which is what happens when you twist it around itself. So it's some operator which has some kind of spin, which we denote by theta A. And the S matrix, which is what is familiar from CFT, which has this kind of graphical representation. And this curly D is called the total quantum dimension. So it's the sum of squares. I will not go into the details of how you derive these representations, but it's a kind of standard material. And this theta, okay, you can think of theta essentially as the T matrix of the CFT modulo the central charge that goes here. But we will always have non-chiral theories, so this term gives one. But in general, you have to be a bit careful. Okay, so now we have to first define what is an algebra inside this category of lines. So what you want? So I want a product, no, on the algebra. So I want some kind of map that takes two of these algebraic objects and maps it into another one. So it's the same object here and here and here. This is not a priori the map that you had before. It's some kind of linear combination, and you can write it in components. So you can project here, here, and here on some simple lines that are in this object. This is okay. This is actually important. So you can always decompose this kind of object into simple lines. No? And I will call the coefficient ZA of B because they're going to be the partition functions, no? Of course. And you can always project this figure on the components, and then you can define some kind of tensor, MABC, which implements this multiplication. So if you want to actually find these guys, you have to find this tensor. And the hard step, in my opinion, is to prove associativity. So now it's not the associativity of the full category, it's only of this object, no? So here you have some kind of, you can write it in components and you get some kind for M. So it's not linear, it's hard to solve. So classifying this object is hard, but since we will see that you can map it in CFT language, when you have done the classification in CFT, you can go back. So that's useful sometimes. But okay, we'll need to remember this kind of decomposition. So this we can always do. Okay, then we said it was commutative. So commutative just means that this anion, this object A, not braid with itself. So because we want to think about gauging, so gauging is like putting a complicated network of these guys in a consistent way. So you want the network to not be sensitive whether you've done this or this at the beginning. And it's just, you can just write here and put it in components. It tells you that essentially these M's are symmetric in A and B modulo the R matrix. These statements are always a bit tricky because there is a gauge fixing procedure. So of course, it's better to do it like this in a more abstract sense, and then just try to avoid going to the components until the very end. Cases, okay, if you have commutativity, you always have that theta is equal to essentially because when you have only one or zero maps, there is a relation that tells you that R is very bad. A, B, C, A is equal, let's say if I get it right, I think it's like theta A, theta B over theta C. So you just put everything equal here. And since it's commutative here, you get 1. And here you get theta. So you say that it's 1, no? Which is okay, useful to keep in mind. Okay, so we're gonna have to talk about gauging. Gauging for us will mean just to put a fine enough mesh of these A objects to glue them together in trivalent junctions, which is good. We have other properties like associativity to simplify and change this network around. And we don't care if it's like this or like this because we have commutativity. So once you have these properties, you can put a network in a consistent way. Essentially, in quantum field theory language, it means that there are no 2th anomalies. So you can essentially, what you do is that you calculate your manifold, you put these lines on the edges, you put this morphism on the vertices, and then you start simplifying, and you get the simplest, like minimal network. But in practice, you never do that. You try to make some more generic statement. So if you have some kind of invertible symmetry, so all the lines in A are have quantum dimension equal 1, so they form a group, then this can think of sum over bundles because you just use Poincare duality and you think of this as some cohomological sum. So it's a sum over gauge bundles instead of lines. But in the general case, I don't know of what is the map into the cohomology. So it's a bit, this gauging it should be taken a bit lightly. It's not clear, but this will be the definition of gauging. So, okay. Another nice way, I think, to think about it is that when you do this procedure, you have something that is a Gauss law. So a Gauss law is just a projector, no, that tells you what happens when you put a line into the gauge theory, or an operator, no. So after a bit of like manipulations, you have to use commutativity. You can write this projector. So in this paper, there is the one for not commutative algebra, but then it's written in many other papers for the commutative one. You can show that this is a map from A times X to X, no? So to think about what it does on, you have to somehow close it down. So now you have and then you put some morphism here to close into some line that is in this fusion. So you put something here, and you put something below, and you study this alternative. So this is what, when you have to think about how it acts on lines, you have maybe to think in this way. But okay, and then you, in the abelian case, I just put the picture because it's like much simpler, because essentially you can simply, in the abelian case, there is these products are trivial because it's a group, and you can just simplify this map. So let's see, let me so I can find something better. Maybe these ones work better. Okay, this. So you have this stuff. This you can. Oh no. The thing on the top, okay, and then you can just use essentially the crossing equations to put it in this form. And when it's abelian, here you get one line, here you get the conjugate, so you only have the identity, so this guy goes away. You have to take care of some normalization factors, but that's all. Here I put k, I should have put the quantum dimension, but this is for Chern-Simons with abelian Chern-Simons with k matrix. And then it's very easy to compute it. In the abelian case, it's obvious, it's just something that projects on A. We'll see this in some examples. But okay, this is maybe the simplest object to keep in mind if you want to think about gauging this complicated algebraic object. You think about the Gauss law and what it does, then you can find essentially anything. Okay, we have to say what is Lagrangian. So Lagrangian is just an algebra which has its quantum dimension. So if I just draw a big line with A here, the A is just sum over A is just this, is equal to the total dimension. So it depends a bit on the convention. My D is the square root. Sometimes people don't put the square root, put a square on the other side. But essentially, this is like the maximal anomaly-free thing that you can gauge. Because once you gauge this, you get a trivial TQFT in the bulk. So, and essentially, there is some theorem that says that and then this matrix is modular invariant, the matrix of the decomposition into simple lines. One way to think about this is the following. So if you, one implication is very simple, no? So if Z is modular invariant, is because you do S times Z equals Z, okay? B. AB is sum over B, no? Here you put A equals 0, so Z0 becomes 1. And here you have to write what is essentially S0B, ZB, but this guy is dB over D, the equation. No, this is this and so on. So that's simple. And the other way is essentially saying that after you gauge, you get a trivial theory, because if you get a trivial theory and you do a modular transformation, so you change the cycle you close in the bulk, doesn't change anything because there is only one state and there are no anomalies. So the matrix will be modular invariant. The point is that essentially present the only state of the gauge theory as a solid torus with the A on the non-contractible cycle. This is the state. So you can see, well, the Z comes in when you just expand it. Okay, so we do an example. So just abelians and Simons, non-chiral, no? And we take the level to have some factors, so 2pq. So this means that it has some zero form symmetry every single Simons. And define some automorphism, this omega, which is only once in Simon's theory, no? And this automorphism essentially preserves the S and the T matrix. So the point is that omega squared is equal to 1. So when you do the T matrix, which for the abelian case is this, equals 1 mod 2k, which is 4 pi q here. Then you just use, you put omega L instead, and you get the same thing, okay? And for this matrix is the same thing, but because abelian theories, they are related. So you also get that S is preserved. And then you take this combination of line, which are the ones in which you act on with omega on the right movers. And the algebra is just the sum over all the lines. So you have all this, the simple case is omega equals 1 is just the diagonal lines, okay? But for every such guy, you can do 1. And then you see that if you braid any line with A, so it's just a sum over the whole thing, you get a delta. Why? Because you will have something that omega squared equals 1 to move the omega from this J to this L bar at some point. Then it becomes a delta. And the partition function for this modular invariant is essentially this guy here. It's like well known. And furthermore, the only guys that remain are those that are in the algebra. And since it's a group for the abelian case, because all dimensions are equal to 1, you can also show that once you do the fusion, this gets absorbed inside. So you can actually just write down the Gauss law explicitly. Here you use the S matrix. You use this formula, and then, okay, when this goes away, you fuse and you get back the A. No, so the Gauss law here just tells you that all the lines that belong to A become A, and the rest gets dropped out. So it's kind of simple. And okay, the link with the modular invariance is just that when you compute the only state, so you put this network, you simplify it on the solid torus, and so you end up with this configuration. You expand it in the basis. Here I forgot a B. Okay, well, it's obvious. And then the function that you get when you put some like holomorphic boundary condition is a modular invariant of the CFT. So that's how you do the link. And this essentially, every time you have some Lagrangian commuting algebra, this works. So you can write these modular invariants. And another nice way to think about it is using branes. So this was discussed first in Capustri and Saulina, and then they discussed in this recent paper. So what is the idea? If you have some topological brane that separates the QFT from empty space, so this is called the gapped boundary condition. You can always take a tube of this. So here, inside there is the trivial vacuum, and then you shrink it and you get some line, no? And you want to identify this with a commutative Lagrangian Frobenius algebra. So you see that all the properties come because the surface resolve the singularity for the product, no? So you can just move around things and get the identities that you need. So that's very nice. So there is this. So you can see essentially that condensing some Lagrangian algebra is like putting some brane in your theory, which is also what people saw in 2D. So it's just a more Now, just to give you a sense of what happens when you try to actually compute this, so why this Gauss law comes about and so on, just take the theory on T2 times the interval, no? So this square is actually a torus, it's closed, and this interval. So actually simplify the network explicitly here. It turns out that you can just put it at some point on the interval, say here, and it's this kind of guy. So it's something that goes like this, and this goes back here. So it's identified. So it's very simple. And then you can say, well, now let's put a complete basis of states in the middle and see what happens to this geometry. How is this related to the separated ones, no? So if you cut around this cycle and put a completeness relation, which is just choosing one cycle to contract and putting the lines on the non-contractible ones, you do this. So you separate, you sum over all the lines, and then you look at this part and you think about it for a bit, and you actually get the expectation value of this Gauss law. Essentially, because this line, if you move it here, you see that is linked with these two components, which are horizontal. So it goes around, and you get. So this is why this Gauss law describes something that's kind of useful to keep in mind. And then you can actually, there is a slightly formal calculation in general. I showed you like the abelian case, no? But you can do it in general. And this shows you that the states you create with this guy, so on the non-contractible cycles, and just Zx times A are the same. So you just substitute it. Here you get A, no? But sum over X, and here you have X. So you do the sum here and you get back A. So you get, now you have factorized your two boundary thing in the single boundary. So it's here, but what you did is that you absorbed all the states that you obtain by cutting into this Lagrangian anion. So you can think in this kind of suggestive way. And to do generic manifold in the abelian case, it's very easy to write down the network. In the abelian, it's harder, but you can think in terms of these boundaries. So you just put the network, you make it fat by putting the boundary instead of the anion, and then you just enlarge it as far as possible. You get this kind of cylinders which have inside your theory, but outside of the anion. And essentially, you can simplify them because the Hilbert space on this guy has dimensions at 0. So it's simple to see. So this dimension is just so this circle with the boundary condition, and you do the trace, no? So you close this circle like this, and you get a torus with the boundary condition around. And then you think of this in terms of a sphere in which you have taken out a solid torus, and then you shrink that to the anion. So you get that this is at 0. I mean, this was a bit weak, but it's a very easy thing to compute. And so you can just put the only state, which is capping off this guy, and you divide the boundaries. So this is a bit less explicit, but it's easier to show for general geometries. And of course, okay, so let's. I think I'm almost out of presentation, so it's. I think it's good. So this was just made to motivate why you should think of this condensation as the alpha eigenstates in the bar gravity. So you see that you get something that factorizes nicely, but you now have a path integral prescription as sum over geometries. And of course, you can also have said everything in a very trivial way by saying you have just one-dimensional Hilbert space, then you just cut everything, and since there is only one state, every geometry is kind of identical. The only the only important contribution comes near the boundaries from the boundary conditions. This is like a way to trivialize the whole thing in one sentence. Okay, this is this comment. So of this kind of background independence that can happen. And you should think of this as some explicit prescription to prepare these alpha eigenstates. So one way to kind of think of this is that if you do quantum gravity, apart from knowing your low energy theory, there might be a prescription that tells you how to sum over defects. And this is some kind of UV data that you have to understand why it comes. But if it works in this way, then you don't have this factorization problem. So it's cured by the sum over defects. But if we just have these simple topological theories, then you will get always these wormholes and these unpleasant things. So, okay, another way to think of this is just to think about global symmetries in gravity, although like in low dimensions, this does not have a generic proof. But in your theory in the bulk, you have some guys which are topological operators and do not see gravity, which are these kind of these Lagrangian anyons, because they are modular invariant. When you sum, they don't care about gravity. So they're like true global symmetries, even if they have gravity. And if you don't break it somehow, you're gonna maybe have some hint of a problem. So if you gauge one, you will, from the onset, get rid of this problem. In this case, it's a bit particular because if you do the gauging, you don't get back a quantum symmetry. I mean, you get it, but there is no charged operator. Usually when you gauge, you get another gauge theory, no? So in this topological case, this doesn't happen, but one has to be careful. So, I mean, this is related to a set of examples. And okay, another comment is that it's nice to like try to streamline a bit this concept, algebraic concepts in quantum field theory. So these kind of Lagrangian algebras have some simple interpretation in terms of having Gauss laws and like normal gauging procedure. And there's a lot of work in this field of non-invertible topological objects. So I think it was nice to learn it. Here are some papers, some of the most recent ones. So let me just conclude with some open questions. So this was like a motivational work, if you want. It says why you have to try to think about this construction. But there are some physical examples that one has to study in a deeper way. So one is like the case of non-compact theory, so SL2R, SL2C, which are the kind of groups that you get when you take gravity in 2 or 3 dimensions and think of it as a gauge theory, you know? This technically is harder to study, but there should be a way to study it with the same tools and understand what happens there. Using this kind of techniques, you can also understand this motivational construction of Maloney and Witten that I presented in terms of the Lagrangian algebras in this Rn theory. So the theory is just completely random, but you can change it. It's not compact, there's no holonomy. And you can actually look at the Lagrangian algebras here, and you see that they're in bijection with the elements of the Narine ensemble. Just do the computation of which are. So here you can invert the result, no? So give some hope. Of course, you have to understand where this condensation comes from. So this is like an important question. So if you do a UV like string theory computation, the theory at low energy looks like some topological theory. Does it come with this prescription or does it not come with this prescription? So is it an ensemble or not? So this, I mean, I think some computation must be done in this case. And another thing is this probability coefficient that I introduced before. It's not clear a priori why they should be positive or negative in this case, but maybe from the bulk unitarity, you can say something. So you can write these coefficients as scalar products in the bulk. So you can like link them to properties of the algebra objects. So you can maybe get some mileage from there. And okay, another thing you can think in 2D to relate this kind of story about gauging to some more recent work on 2D gravity without the factorization problem. So there are some pictures that look similar to what we wanted to do. And but you have to deal with this non-compact theory. So there is some technical difficulty, but I think we're going to start looking to this. It seems to be within range. Okay, so I finished. Thank you.
Okay, do we have questions? Okay, so if not, let's thank Christian again. Oh, sorry, we have a question.
I think we have a bit of time, no, because it started a bit late. Like,
yeah. So just some maybe a random question. So this reduction, I mean, here I understand that somehow the condensation removes the entire symmetry, even if it is non-invertible. But there is some work regarding these gravitational solitons reducing the non-invertible symmetry to a group-like symmetry, right? Like maybe Jacob McNamara's paper. So does it have any similarities with that case, or?
So you say that you can consider other algebras and what you get instead of being the trivial TQFT is an abelian one? Is this the question?
Yeah, I think the idea was that somehow in gravitational theories, you can construct objects, which even if you assume some non-invertible symmetry, that existence of the objects directly will just break that symmetry to a group-like symmetry. But here, I guess you are completely removing the symmetry by condensing. Because
yeah, essentially, yes. But because we don't see this kind of object, no, this is already the effective theory. So maybe what happens is that that thing, you can rephrase it in this way if you look at low energy observables in some cases. But definitely, I mean, there is more work to do to understand how the mechanism actually is put into action. The only thing that we will try to kind of put forward is to explain why, like, use these concepts which are maybe not very familiar to people that study this kind of problems in gravity, and why this is a natural thing to think about and how it helps you. But one needs also to do more work. So this kind of just the beginning, maybe.
And maybe a more concrete question. So here there's what fixes which A we should condense. So when we take a particular CFT and average over them, does that the partition function of the CFT should then fix A, right, in this description, or?
Yeah, essentially, okay. If you condense one A, the dual is going to be a fixed CFT, no, well-defined thing. So if you know that, you're fine, no, because that tells you which you have to condense. But what tells you which CFT from the bulk is not clear. Just without thinking about what we want as a boundary dual. So I think maybe there has to be some more data that comes from UV physics or whatever, something outside this kind of toy model description, which chooses, I mean, if you have more than one A, it's like having various ground states even in presence of gravity. And some has to be chosen by some mechanism. So you have to resolve this degeneracy somehow. But I don't know, like it would be nice to understand how this works.
Thank you.
More questions? Okay, so let's thank Christian.